Differentiating schizophrenia from bipolar disorder relies on years of subjective, longitudinal behavioral analysis. A physician observes the patient over time, waiting for specific clinical manifestations to appear and hoping the initial assessment holds true. But those initial assessments are frequently wrong. Up to 50% of schizophrenia cases and 70% of bipolar cases are initially misclassified, leading to years of incorrect pharmacological treatment. The biological alternative relies on the sentinel principle. Because the peripheral blood acts as a liquid biopsy for the central nervous system, a specific mRNA expression signature can accurately separate the patient cohorts. The engineering goal is to build a single automated desktop molecular diagnostic instrument that takes one venous blood draw and renders a differential psychiatric probability right at the point of care. The actual biological science is already complete. The 18-gene biomarker panel and the classifier algorithm are proven and patented by Laguna Diagnostics. The barrier to putting this device in a clinic has nothing to do with scientific discovery. The barrier is strict physical execution. Taking a multi-step, lab-grade psychiatric blood test and forcing it into a desktop form factor requires automating highly sensitive chemistry, thermodynamics, and optics. It is purely an integration nightmare. The proposed instrument, the SC meter, breaks no laws of physics. Every major piece of required hardware is already available off the shelf. This component list proves the compute logic relies entirely on accessible development boards, like the Verdin or Raspberry Pi. Extreme optical sensitivity is handled by existing commercial photomultiplier tubes, and aggressive temperature control relies on standard thermal-Wightech Peltier cooling technology. Even the power supply and connectivity hardware are built from standard medical-grade commercial parts. The chemical processing agents are equally accessible. Extracting the RNA from the raw blood sample uses standard silica magnetic beads. Since every single physical component can be sourced today, the intellectual property and defensible value of this machine lie entirely in forcing these parts to function flawlessly together under strict tolerances. A standard binary point-of-care test only has to detect if a specific pathogen is present or absent. A differential psychiatric diagnostic is much harder. It requires the precise relative quantitation of specific human transcripts. This equation illustrates how the machine calculates that relative transcript abundance. The variable CT is the threshold cycle. This is the exact moment the target's fluorescence crosses the background threshold during amplification. The variable E is the amplification efficiency. An error margin to work perfectly, the system assumes the target template doubles 100% every single cycle. Exponential math is brutally unforgiving. A 5% drift over 35 cycles will distort the final template estimate. That single distortion invalidates the final step of the process, corrupting the downstream locked logistic regression model that calculates the probability. An error margin this large can cause the algorithm to falsely flip a schizophrenia diagnosis to a bipolar diagnosis. The abstract math dictates unrigid physical reality. The machine must hold external physical variables absolutely tight, or the resulting psychiatric score is entirely untrustworthy. The mathematical requirement for perfect amplification efficiency translates directly to extreme physical constraints on the thermal subsystem. The hardware must maintain a spatial uniformity of exactly plus or minus 0.1 degrees Celsius across the entire multi-target array simultaneously. To equalize the efficiency across all 18 target genes, the thermal block must execute aggressive ramp rates, heating at 5 degrees per second and cooling at 3 degrees per second. Generic heating elements cannot execute that profile without overshooting the target. The system requires high-end, custom Peltier microheaters to snap to temperature and hold it. Moving to the optical subsystem, calculating the exact threshold cycle, or CT, imposes an equally strict hardware demand. The sensors have to accurately plot the fluorescence of very low-abundance human transcripts across multiple dye wavelengths, including FAM, Hex, ROX, and Psi5. Cheaper photodiode arrays produce too much noise. The device requires highly sensitive, low background readings to establish a clean baseline. Custom firmware is required to instantly track this fluorescence, enforce calibration linearity thresholds, and actively flag out-of-spec runs before they generate false clinical probabilities. To prevent the sensors from drifting over time, the system requires integrated internal calibration standards physically built into the test. The hardware exists for one purpose: locking temperature and light tight enough to feed pristine data into a locked regression model. Before any thermocycling or meth can even begin, the raw, chaotic environment of venous blood must be processed, down into a clean cDNA load on the cartridge. This workflow requires aggressive upstream chemistry. Guanididine is used to lyse the whole blood and immediately denature destructive RNase enzymes that would otherwise chew up the target RNA. The process relies on solid phase extraction. Silica magnetic beads bind the target RNA, while proteins, genomic DNA, and inhibitors are washed out of the channel. The system must execute a precise low-volume elution, concentrating the genetic template strictly into the sensor's linear range without over-diluting it. Traditional liquid reagents require strict cold chain shipping. Relying on refrigeration destroys the logistics of the point-of-care business model. The engineering solution is to pre-spot the necessary primers and probes into a dry stabilized glassy matrix of trehalose and xanthan directly on the cartridge. The lyophilized single-dose enzyme beads are stored dry on chip. They are reconstituted at the exact moment the run begins via automated microvalves. Automating this violent, precise wet chemistry on a mass-produced injection-molded plastic cartridge is the absolute prerequisite that makes the downstream math possible. Successfully engineering a working novel machine does not inherently give the builder the legal right to sell it or use it for diagnostics. We can visualize the intellectual property of the SC meter as a three-layered stack. The base layer is a design patent, protecting the ornamental appearance of the housing and the redundant color-coded graphical user interface. The middle layer is a regular utility provisional application. This protects the novel hardware architecture, thermal control mechanisms, and integrated microfluidics. The top layer is the biological operating environment that provides the medical utility. This top layer consists of the 18-gene biomarker panel and the specific locked classifier coefficients, which are already owned by Laguna Diagnostics. This highlights the principle of freedom to operate. Device patentability and biological inventorship are entirely separate evaluations. Because natural genes themselves cannot be owned, the IP at the top of the stack relies heavily on the novel application of this specific combination and its unique regression coefficients. Beyond the licensing, the final, often hidden barrier to commercialization is the massive non-recurring engineering costs required to validate a pre-prototype concept. The program requires rigorous, accredited electrical safety and EMC testing under IEC 60601-1-2, alongside expensive contract embedded engineering to lock the firmware under a proper quality system. Furthermore, translating the original assay from a lab-based exon array to this new qPCR hardware requires separate, extensive analytical and clinical validation. The risk profile of this diagnostic tool is a complex negotiation of hardware tolerances, software validation, and licensing agreements. True innovation in modern point-of-care medtech relies on the brutal, rigorous integration of chemistry, thermodynamics, optics, and IP law to automate complex math right at the patient's bedside. Successfully engineering a working, novel machine does not inherently give the builder the legal right to sell it or use it for diagnostics. Visualize the SC meter's intellectual property as a three-layered stack. The base is a design patent, protecting the housing's appearance and the color-coded user interface. The middle layer is a utility provisional application, protecting the hardware architecture, thermal control, and microfluidics. The top layer is the licensed biological operating environment, providing the medical utility. This top layer consists of the 18-gene biomarker panel and the specific locked classifier coefficients, which are already owned by Laguna Diagnostics. This highlights the principle of freedom to operate. Device patentability and biological inventorship are entirely separate evaluations. Because natural genes themselves cannot be owned, the IP at the top of the stack relies heavily on the novel application of this specific combination and its unique regression coefficients. Beyond the licensing, the final, often hidden barrier to commercialization is the massive non-recurring engineering costs required to validate a pre-prototype concept. The program requires rigorous, accredited electrical safety and EMC testing under IEC 60601-1-2, alongside expensive contract embedded engineering to lock the firmware under a proper quality system. Furthermore, translating the original assay from a lab-based exon ray to this new qPCR hardware requires separate, extensive analytical and clinical validation. The risk profile of this diagnostic tool is a complex negotiation of hardware tolerances, software validation, and licensing agreements. True innovation in modern point-of-care medtech relies on the brutal, rigorous integration of chemistry, thermodynamics, optics, and IP law to automate complex math right at the patient's bedside.